I'm very excited to have Scott give a guest lecture today with us. So Scott Reed, he's a founding member of the Generalist Embodied Agent Research Lab at NVIDIA. And before that, he studied generative models and generalist agents for 8 years at Google DeepMind. For example, he's also very well known for leading the Gato paper, the generalist agent paper, a few years ago. And he completed his PhD at the University of Michigan in 2016 under Hong-Lek Lee. And we are very excited to hear about your talk and latest research, Scott. Please give him a warm welcome.
All right, thanks for the intro, and thanks, Oier, for having me here. Very excited to speak to you all, and I'll begin. So the talk I'll give is about backbones for robot learning and the major choices that we can make here and emerging paradigms. So VLAs, world action models, or from scratch. What's the right backbone we should use for embodied agents? First, a little bit about me. So I'm from Michigan. This is actually just really the intro blurb, but I was at DeepMind for 8 years doing work on generative models and generalist agents, and has 2 years on the gear team led by Jim Fent and Yuka. And there's a family and a new guy there just joined, and that's me. So what do I mean by a backbone? So for this talk, I mean the architecture that encodes robot sensor data, cameras, proprioception, and also the language instructions, encode all of those things into some shared representation that can be used for action prediction. So this backbone, it determines not just how the policy runs at inference time, but how it's able to soak up knowledge during pre-training and transfer that to downstream tasks of the robot. And the major choices here that can be made is, one, just go from scratch, just train some bespoke architecture just on your robot data, which could make sense if you have a lot of it, or if you just care about some narrow task on a particular embodiment. It's not very open-ended. Over the past 5 or 10 years, the dominant paradigm has actually been more to use pre-trained foundation models instead, or at least initialize from them. And the major choices here would, of course, be to use VLM, like a vision language model, which might have been used for things like visual question answering, or the emerging paradigm is to use video models, or there's different names for them. Some people are calling them world models, but basically the lineage of these things is from video generation, and turn that into a backbone. Of course, video diffusion models have been around for a long time now, a few years, but I think only recently have reached a stage of maturity in terms of their quality and also in terms of the architecture that would support them being a backbone for robotics and other embodied agents. So the agenda, I'll first give a brief survey of VLAs and have some commentary on those, and then world action models, and then discuss training from scratch, both the historical perspective and some more recent exciting developments there. And then we can conclude with discussing future directions and have some Q&A. So what are the key papers in VLAs? So of course we have the robot transformer series like RT2, OpenVLA, the Pi models, Pi 0, Pi 0.5, Pi 0.6. The group models we did at NVIDIA focus more on humanoids, TRI's large behavior model, and then Gemini and many others. These are just the ones I'm most familiar with. And the key principles here, the good things about them are it puts everything into a unified modality. They tend to support cross-embodiment well. You can just directly fine-tune VLMs to generate control tokens. There's a lot of diversity here in terms of how they represent actions. Some use discrete, some use continuous and do diffusion or flow matching, And the great thing about them is that they can leverage internet-scale data for reasoning and grounding. And in terms of the generalization, there is some evidence that they outperform from scratch imitation learning. By training on multitasking, multi-embodiment, they actually are more data efficient and have higher top-end performance than training from scratch on a single task or a single embodiment. So what do the architectures look like? So I'll just show OpenVLA first because that's the simplest one, and then people may be familiar with this. Basically, you have some pre-trained vision encoder like Dino or Siglip or both to encode language and vision, and the instructions are encoded with some pre-trained language model. And this whole thing might be frozen, at least at first, and then you learn to detokenize that into actions. In this case, the actions are just discretized with binning, and then they'll later be detokenized into the continuous values when you actually want to run the policy. So this is just a very simple architecture that actually turned out to work quite well. There are fancier things you can do, like the Pi models have both a discrete and continuous action prediction. So they have this thing called fast tokenizer. They have some kind of Fourier basis to encode the tokens so that the VLM can be co-trained with both language tasks, like predicting subtasks, while at the same time predicting actions. This turns out to be a great thing for pre-training because it turns out that if you had just tried to co-train directly predicting discrete language tokens and then also backpropagating flow matching or diffusion gradients through your VLM, this would destroy your VLM weights. And so you would lose things, you would lose properties such as language following. There might be ways to do it if you carefully train in stages, but there's always a risk of catastrophic forgetting once you just naively try to co-train on VLM language prediction tasks and robot action prediction. So by doing everything with discrete tokens, it would open up a lot of options for how to do the pre-training and to end up with better representations in your VLM for control. However, there is still a benefit to having this like separate diffusion or flow matching action expert because in some cases when you decode your discrete action tokens, you may have decoding errors. This is one of the problems with FAST, and you can imagine that this could cause safety issues. Like what if if your decoded action is somehow undefined, it's an error, and it just generates some kind of default position target for your robot arm, you could imagine the arm just flinging out and doing something really dangerous. So for both safety reasons and probably also for performance reasons, it's still good to have this flow matching or diffusion action expert, because you'll never have decoding errors there. And there's a lot of other VLAs with diffusion decoders, so like Pi, all the group models. This is the TRI. They call it large behavior model. I think it's just an alternative name for VLA. I also like large behavior model as a name. And this one also takes pre-trained VIT, like image and language. They have a simplified architecture here where actually they're just concatenating the image tokens and the language tokens and going straight to the DIT. That actually works surprisingly well, at least on their suite of tasks. And the great thing about this paper, everyone should read, they do a really rigorous study of like, not just wishful thinking, but really examining, does multitask pre-training VLA style actually improve downstream task performance? Does it improve data efficiency and top-end performance? And they find that it does pretty significantly. But they had to do very, very careful analysis due to the difficulty of real robot evaluation. They needed to do things like double-blind evaluation. So you take pairs of policies, have evaluators actually not know which one is which one, and compare them head-to-head and then the same robot at the same time. And doing careful statistical analysis to make sure that the results were statistically significant. And yeah, the findings do back up a lot of the intuitions that people had about VLAs, but it's great that someone actually did this very rigorously. And I think there's a lot of great lessons in that paper. And so here's some of the cool demos that I find inspiring from VLAs, the VLA era, so like Pi 0.6, basically the Pi model with RL post-training, making special things for like over an hour, almost an hour. I found that really, really impressive. Here's one from Nvidia. It's called Ego Scale. This was built on the Root M1.5 architecture, and they used a lot of actually human egocentric data with hand tracking. And that data in particular is what I think made this recipe work very well. And so VLAs can control bimanual parallel jaw gripper, that can control like humanoid hands really well. They can also control humanoids when you combine them with a whole body controller. So VLAs are now finding applications in all kind of different robot form factors, and yeah, starting to really mature as a model class. So what are the strengths? You get semantic grounding from pre-training. New task learning is data efficient compared to going from scratch. And there seems to be predictable improvement as you scale the model and the data, assuming you have high quality data to scale. And there's some evidence of cross-task and cross-embodiment transfer, but I would say it's far from solved. There are some weaknesses, like the prediction and reasoning are happening in your action space, which might be language, it might be the continuous space where you're doing diffusion. That might not be the right place to do reasoning about physics or control, actually. It may not be the optimal way to do that. The action representation is typically bolted on in some way after pre-training, and there's always a risk of catastrophic forgetting during fine-tuning. There's this expression, data islands. Due to the lack of lots of web scale data for robotics, we have this intuition that we should just throw all the robot data from different embodiments together. So that's called cross-embodiment. But it's likely that the model just sees these as completely separate islands that from which there's not much transferability, or that the transferability is limited due to the difference in form and correlational structure in these subsets of data. And the evidence for like zero-shot distribution, zero-shot generalization out of distribution between new embodiments is limited or non-existent in my opinion for contemporary VLAs anyways. So what's the emerging class of policy models that have made people excited? World action models or video action models. So some popular instantiations that came out recently would be Dream Zero, Cosmos Policy. Some older ones actually is the GR1, GR2 from ByteDance, and probably a bunch more coming out and have come out in recent conferences. These are just the ones I'm mainly familiar with. And what's the paradigm shift here? We want to predict the world state in pixels, either before acting or jointly with acting. And so we can do prediction and reasoning in a much richer space that may be more suitable to control. Also, I would highlight that the pre-training objective may allow the policy to just soak up a lot more relevant information during pre-training than just action prediction. We can just squeeze a lot more juice out of the data that way, in my opinion, than we could if we were just predicting actions only. So what do these architectures look like? So here's the Dream Zero architecture. There's going to be some VAE to encode the video frames into latents, concatenate them with action embeddings, condition somehow on language, and we have some a block causal DIT, so that this allows us to have caching, heavy caching during inference, so that we can do efficient sampling of frames in action when we want to run the policy. In Dream Zero, we actually have some joint flow matching of both action and future chunk of frames. actually in Dream Zero, you can choose to jointly diffuse both fully, or they have something called Dream Zero Flash, where you just do one step or two steps, where you don't completely actually denoise the future observation chunk, and you just focus on the action chunk, and that actually turns out to perform just as well. Among the different video model-based policies, there's a few different ways to get actions. Some of them will actually fully sample a rollout and then use some inverse dynamics model to recover the actions. Some of them are doing planning, and some of them just use the video prediction pre-training as a pre-training technique, and they don't actually need to fully diffuse the future observations during inference time. And I think there's an interesting analogy to reasoning models in VLAs. We see something similar there, where a lot of the benefit from doing reasoning is that you just did it during pre-training. You learned a better representation that way, and the best thing to do probably still is doing reasoning at inference time, but even if you don't, having done it during pre-training makes your model better, gives you better representations. And something similar is true, I would say, for video models. Another one that came out around the same time was Cosmos policy. Very similar idea, but with some interesting differences. In addition to predicting just actions and images, future images, they also diffused future proprio and value. So I think this paradigm is actually quite flexible. And maybe this paper could even have a stronger claim to being a proper world model, because it's just modeling a more complete set of things in the world of robots. And the way that their architecture looks is also quite interesting. The design choice they made was to encode to embed proprio and actions and value into the image embedding space and just tile it spatially. So that way, from the perspective of the diffusion models, everything is vision. You just have some special types of frames for action, proprio, and value, in addition to the robot camera data. And the model just figures it out, as neural nets tend to do when you give them enough data. And also, a very different paradigm that actually came earlier was autoregressive world action models like GR1 and GR2 from ByteDance. And these are like interleaving models that interleave language, robot state, image, and just predict everything. And they also have some pretty encouraging, impressive results long before other teams kind of came to this paradigm. And I think this could be scaled and pushed quite far as well. Actually, this is more of the kind of flavor of model that I worked on previously of Gato, which is just a big transformer language model training on all the robot data. Just kind of have some way of canonically serializing all of your sensor data and camera data into a flat sequence of tokens and model that with a transformer. They make some clever design choices here and push it way further in robotics, but it's kind of that school of thought of like one big transformer for everything into a flat series of tokens. I think that can also be pushed quite far. Here's some WHM demos from Dream Zero that I found pretty impressive. The cool thing about these is none of these behaviors were in the robot training data, although it may have been shown by humans in the pre-training at some stage of the video model. So it can do things like untying boxes, pulling carts, pull a straw out of the cup, shirt ironing. I don't know if it's really actually ironing. It's not actually doing ironing, it's going through the motions. So you can see how this can be pushed further and hopefully become genuinely useful at some stage of development. So diving deeper into Dream Zero, we can look at what the generated videos look like. So here's like untying the box. It's obviously not pixel perfect, but it's generally it's generally consistent with what the robot actually does. What we tend to observe with these models is that performance in terms of the sample quality, and the success rate scales with model size. So when we used like the 14 billion parameter WAN model, it was way better than the 2B, and both for the samples and the success rate. And doing some failure analysis, we see most failures stem from video generation errors rather than action prediction. So whatever trajectory the video predicted, that's what the policy ended up doing. And this suggests something exciting, which is that improvements to the video backbone can directly translate to better WAN performance. So whenever we see holes in the policy and errors, if we just kind of improve the video model there, we can expect that the policy will improve. And also, it doesn't necessarily require that we have robot data to fill in those gaps. It could be human data. This gives us one promising path forward in robot learning. So the strengths of WAM, I would say that they naturally learn some kind of intuitive physics from pixels, and it gives us a much more scalable source of pre-training data. If most of the juice is just coming from predicting camera sensors, we just need to give a lot of data from cameras. And it's embodiment agnostic in a sense due to the unified output space for prediction and reasoning. There's less of a tendency towards data islands because everything shares the same form of correlational structure that you're predicting. But they have some weaknesses, like they're very expensive to sample compared to VLAs. Modeling every pixel is probably overkill. I mean, we're not doing it in pixel space, we're doing it in latent space, but it's a type of latent space that was learned to compress pixels but still be able to reconstruct them. Right? So, we're taking the latent space of video diffusion models that ultimately have to produce aesthetically appealing high visual fidelity. That still may be overkill for robotics. And there's a lot of papers showing that if you care about just one domain, like Minecraft, for example, you could train a much more compressed tokenizer or VAE just for that space, and train a sequence model on that, which generalizes well and is much more compact and could run much faster. If we care about like really open domain robotics, it's not clear that we can compress it that much, but I do think that's a promising area of like, if we just are doing control and we don't ultimately care about generation, is there some modification we can make to these tokenizers or VAEs used by WHMs that just compress them a lot? And there's a lot of exciting research happening here. I think the answer is yes, but we need an approach that is robust in general and kind of plug and play. And then I think that'll drive a further cycle of improvement in WHMs. Also, context length is currently limited in most contemporary approaches. Again, there's tons of cool research happening here. I think it's just a matter of making it really simple for people to use and scalable without sacrificing performance. So how do we extend context length? So the third paradigm is training things from scratch. Here's the main papers that I think about in the robot policy from scratch genre, going way back in time to like the DQN days, before the foundation model era. Like everyone just trained some bespoke network on like one task, and of course people have the idea, what if we train one big network on all the data? So I would say Gato, Octo, RT1 are of this concept. So in Gato, we even took like text and images and VQA tasks along with Atari and robotics and just tokenized everything into one big transformer. And you can do that, and you can do that with robots as well, whether it's single embodiment multitask like RT1 or many tasks like RTX and Octo. There is this tendency to learn data islands which limit the generalization. I would say there's some generalization in all of these, but still limited by this data island phenomenon. And we do tend to, I think that this approach, we do tend to hit a limit of just how many embodiments, how much data, high quality data you can get from like a data consortium, or just like in my case, harvesting all the data I could from DeepMind sim agents and a few robots. It's kind of bounded by like researcher time. So what are the modern approaches to like from scratch? So really exciting things happening with UMI, Universal Manipulator Interface, like Generalist AI and Sunday, of course, and other companies. I just included just some for examples. they're doing large-scale image-based pre-training. I think they said they have like 500K hours, something crazy like that. So with these sensorize the humans. If you add sensors to the humans, you can gather really high quality really high quality demonstrations, which transfer directly to the robot. Another approach is just to not even have sensors, but use cameras to do annotation of data of like humans doing things in the wild. This is ego scale from DeepMind. We only had 20K hours, but it could easily be scaled way more. And with a small amount of like sensorized data, like 50 hours with a vibe amount of flow, and like a tiny amount on the robot data, we see pretty impressive results. So both of these kind of approaches are showing scaling law type behaviors, where you just increase the human data, you see a continuous decrease in the validation loss, and you see a monotonic increase in the success rate. So both of these papers, they take a very different approach, but they're both saying with human data, not scaling robot data, scaling human data, which scales much better, from scratch can actually work. And so you could think about training a foundation model without having to chain yourself to either VLMs or radio models or anything. You could do whatever architecture you want. The architecture may not even matter. So concluding thoughts in some time here, what I'm really bullish on these days is world action models, video action models for their generalization properties, and also scaling human data, which could be sensorized or only partially sensorized. I think putting these two together will take robot learning a really long way, and I'm excited to see the great work everyone does on this. And thanks everyone for having me here, and I think now I can pause for some discussion.
Hey, so you mentioned that you think that predicting the latent space of a VA designed to, like, for video generation might be overkill. Do you think predicting the latent space of like a JEPA model or something like that might be more efficient?
Yes, I think so. Yeah, latent world models are a very promising direction. I don't know if I would like make a big bet on them right now, because I think we still need to figure. We don't know exactly what are the right features for robotics. We have this intuition. Many of us have this intuition that pixels are overkill, but at least they are sufficient. There's probably a lot in there that we don't need, but we don't know exactly how, like, we don't know how to cut it down to the minimal subset of features that are needed. So yeah, I think JEPA and other latent world models are definitely in the right direction. But yeah, it's unclear that they've solved it yet. I think more research needs to be done there.
Hi, thank you for the presentation. You mentioned that at some point these video action models should get better with the quality of the video generation. But maybe there is an alternative conclusion, which is that the action conditioning doesn't work. How do we ensure that it's not the action conditioning, but the quality of the video model that is the problem?
The action conditioning, you mean like for if you're doing some kind of rollout and you're doing planning with the world model, or how do you mean the action conditioning here?
I meant the slide showed that the action prediction actually worked, but the generated video was bad, and these were the failure cases. So the problem could be either that the video model is bad, or that the action is out of distribution, or not well. The video model is not well conditioned on this action. Yes.
We need to kind of decompose these problems. There are cases, I think there could definitely be cases where the video is perfect and the model is just unable to find the right action that explains that video. But typically we saw, when working on this paper, that most of the failures, we can correlate the task failure with the low quality video. Like the video will actually show it. The robot tends to at least try to do the gross motor actions that follow the video. But you can see with the quality of these videos, if there's some kind of very, very fine-grained manipulation, then it may not, that information may just not be in the video. So I think at the very fine-grained manipulation level, there is still the problem of just generating the actions, which can be disentangled from the video generation itself. But I think as video models get higher and higher quality, they'll capture more and more fine-grained motions, and I would expect like the correlation between video failure and action failure to be even tighter.
Hello, I have two questions. So, do you think that simulation will be redundant and that world models will be enough to basically capture all of the world's physics and dynamics, and that also RL, so like online and offline RL on top will like with scaling not be necessary? So like you think it's just like a scaling issue and the current architecture we have is enough to capture everything? And also, do you think that video alone is sufficient? Like you said, sensorized human data. By that, do you just mean like ARIA glasses, like capturing where the hand is, or do you also mean like tactile feedback? Do you think that tactile force can be completely inferred from video? Do you think we still need hardware to collect that kind of human data?
Yeah, a lot of great questions there. I'll try to go through them one by one. So for SIM, will SIM be redundant? I think not anytime soon. I do think that like neural-based SIM will be very helpful for manipulation and may displace some of the role of like SIM manipulation, although I'm sure there's a lot of people who would disagree with me on that. But I think like contact-rich manipulation, deformables, and this kind of thing might be where neural-based sim can shine, and we can do like learning in that neural simulator. But for things like whole body control on humanoids or quadrupeds, this kind of thing, I think Sims, I doubt that Sims is really going anywhere. I mean, just the efficiency of the human handcrafted Sims is so amazingly high that, and the cost, the expense of running these world models is so expensive that I wouldn't expect them to overtake human crafted Sims for those anytime soon. But who knows what research will come out on that next. But yeah, I think there's a role for both sim and neural sim for some time. Are there other questions on like force sensing and tactile? Yes, I think when it comes to sensorized humans, I do think we should collect at least some amount of those. I don't know, like I think Ilya Sutskever had this argument that for language models, do they have a world model? He says, well, I mean, if you are training a model on enough of like, the entire corpus of English text or web text, and you really want to predict the next token with just maximal accuracy, implicitly in the model, you should have some world model of like how to explain what's going to happen next, which would require some deep understanding, maybe even of physics, maybe even of things that you would think would require embodied experience, but if you just drive down the perplexity, if you just drive down the loss of this language model, a better model would sort of by construction have this model. So I think the same thing is even more true for video prediction models, like things, all kind of forces that are not explicitly in the pixels may be latent in the model. If it's good enough model of predicting those things, there's all kind of correlates of those forces in the pixels that you're predicting. And so if you want to do a good enough job, that video model must have those features in them, and we just need to elicit those features. We need ways to probe and elicit those features. And so if that's true, I still think we need a lot of sensorized, didn't have to censor on the humans and the collect data, but maybe only like, maybe several orders of magnitude less than we need of the pixels. Like the ego scale, like the way they did it is, I think, informative. Like they had 20K hours of just in the wild with chemical detection. They only needed 50 with Vive. Like Vive is tracking the wrist, and Manus Glove is tracking the fingers. And you can imagine like adding tactile as well. Like probably that's kind of what I'd expect. Is like the tactile is there, but it's only a small amount. And it's really the point of it is like to elicit those features that were already in the world model that will kind of learn mostly from video.
You talked about that, policy performance will now scale with video prediction performance, for example, and then also with the scale of the data. Do you think the future of exciting robot policies will only be, or we will only see exciting policies from companies in the future, basically, because there's so much capital involved in training all these nice video models and collecting all this data, or what's the future going to be?
No, I think that exciting things are going to happen from academia and big companies and small companies. I think that, a lot of times great ideas come from having constraints, and I think we will see amazing stuff, including really high fidelity, cool interactive video models from labs and companies of all scales, I think.
So GPU, if you want to train backbones, that takes a lot of GPU hours, but there are also other problems that you might be able to solve in robot learning and that require less GPU hours. So which problems would you look at if you're more constrained as a researcher?